Okay, so we've got a question here. This is for linear algebra. To those ones who are doing advanced engineering mathematics, you might have encountered this kind of a question. What do we have here? So they say diagonalize A, and this is matrix A. It's a 2 by 2 matrix, if possible. So how are we going to diagonalize this kind of a matrix? All right, so the first step that we have to do here, okay, but by the end of the day, what are we going to achieve? How do we diagonalize a given matrix? So to do that, we need to make sure that we find a particular matrix, let's say matrix P, right? Such that if we take that matrix and multiply by A and also multiply by the inverse of that matrix P that I'm referring to, by the end of the day, we must get what we call a diagonal matrix, where the diagonal of that matrix consists of the eigenvalues of this given matrix. So how are we going to diagonalize this given matrix? So step number one, we need to find what we call the eigenvalues. How are we going to calculate the eigenvalues? Remember, to calculate the eigenvalues of this is given by lambda squared minus sigma of lambda plus delta is equivalent to 0. Maybe someone can say, what is this sigma for? And what is this delta for? So in this case, where this sigma is equivalent to the trace, right, of matrix A. What do I mean by the trace of matrix A? So the trace of matrix A here is basically equivalent to the sum of the leading diagonal. So if we add the elements in the leading diagonal, we get the trace of A. So how are we going to calculate the trace of A in this case? We're going to say minus 5 plus 10, and straight away this will give us positive 5. So obviously our sigma here is 5. What about delta? So delta is also equivalent to the determinant, right? The determinant of matrix A. How do we calculate the determinant of this given matrix? So remember, if you want to calculate the determinant of a 2 by 2 matrix, or what you simply need to do is to multiply the elements of the leading diagonal, which in this case is going to give us minus 5 times 10, right? Minus, we subtract with the product of the elements in the other diagonal. So if you say minus 6 times 9, we say minus 6 times 9. So straight away, this will give us minus 50, right? Minus 6 times 9, we get minus 54, right? Times minus, we get plus 54. So ultimately, minus 50 plus 54, that will give us positive 4. So our characteristic equation, right, is now lambda squared minus, who is sigma? Remember, we've realized that sigma is the trace of the given matrix, and our sigma here is 5. So we get 5 lambda. Plus, what about delta? So we've realized that delta is the determinant of a 2 by 2 matrix, which gives us 4. So this is straight away equal to 0. So by factorization here, if you factorize, you realize that if you plug in lambda there and plug in lambda there, you get minus 1, and here you get minus 4. So straight away, you can see that our lambda is equivalent to 1, or our lambda is equivalent to 4. So this is quite interesting because this matrix meets the criterion for diagonalizability. What do I mean? If you look at the eigenvalues that we have are distinct. So the fact that our eigenvalues are distinct, hence we can also find the associated or the corresponding eigenvectors. So to find the corresponding eigenvectors, I've got another video that I've explained on how we calculate the eigenvectors. So in this particular case, if you want to calculate the eigenvectors, or what you now have to do, like you see here, we've got this particular matrix. So if you say 5 minus 5 minus 1, right, you are going to get a particular matrix here where you multiply with an eigenvector, say maybe k1, k2, and you equate that to 0. So which matrix are we going to put here? So we go in the diagonal matrix, we say minus 5 minus 1, we get minus 6. So obviously we keep these ones as they are. So this becomes minus 6, and this one also it's minus 9. But what is 10 minus 1? Obviously, that gives us 9. Right? So if we try to solve this one, straight away we will realize that K1 and K2, right, will give us what? Will give us 3, 2. Right? What about if we let our lambda to be equal to 4? What's going to happen? So we're also going to form again another matrix. So if I say minus 5 minus 4, we get something like minus 9. Remember, these ones, they don't change. So you can keep 9 as it is and minus 6 as it is. So you can also ask, what is minus 10 minus 4? So that will give us 6. So we multiply with another second eigenvalue. Let's call this one K1 bar and K2 bar, all right? So by the end of the day, we can realize that our K1 bar and our K2 bar, which is the second eigenvector that is associated with this eigenvalue of 4, will give us 1, 1, right? So by the end of the day, we now have this as the eigenvalue and as our eigenvector, and this is our second eigenvector corresponding this eigenvalue of 4. So from there, we now need to form that matrix P. So who is going to be matrix P? Matrix P is formed by combining the columns of these eigenvectors. So we're going to get 3, 2, and here we're also going to get 1, 1, right? And then we multiply that by A. Who is A? A is this matrix that we have here, which is minus 5, minus 6. We also have 10, 9, and 10, right? Here we multiply by the inverse of this matrix P that we have formed by combining the columns of the eigenvectors. So what are we going to get? So if I try to calculate the inverse of this one, how do we calculate the inverse of a 2 by 2 matrix? So remember, to do that, you swap the elements of the leading diagonal. So 1 is going to be here and 3 is going to be here. And then you change the signs of the elements in the other diagonal. That's going to give us minus 2. And this one is going to give us minus 1. And then after that, we multiply by the determinant of that matrix. So if you say 3 times 1, you get 3. 3 minus 2, obviously you get 1. So this is just the same as to say 1 over 1. Obviously multiplying by a scalar which is 1 will not change anything. So there's no need for me to write that, right? And lastly, so now if you take this, which I can call maybe matrix P, and multiply by A, right? And also multiply by the inverse of P, by the end of the day, we'll get the diagonal matrix. What is that diagonal matrix? That diagonal matrix is formed in this diagonal. We put these eigenvalues. So we've got 1, we've got 4, and all these elements become zeros. So yes, we have successfully diagonalized matrix A. Why matrix A was diagonalizable? Because it satisfies the criterion that as long as if these eigenvalues are distinct, you can then find also the distinct eigenvectors. So when lambda is 1, we got this eigenvector. When lambda is 4, we also got this eigenvector. And combining the columns of these eigenvectors, we get that matrix P, such that if that matrix P is multiplied by A and also multiplied by its inverse, we get the diagonal matrix. That's how we diagonalize a matrix, if it is diagonalizable. But in other words, you may find out that some matrices are not diagonalizable, especially if we don't have distinct eigenvalues or eigenvectors respectively. That's it. Awesome.